Group 13 elements, the Boron family. Group 13 elements: boron, aluminium, gallium, indium, and thallium are group 13 elements. Occurrence: boron never occurs as a free element, but always as a compound. Boron is a fairly rare element, mainly occurs as sassolite, orthoboric acid, H3BO3, borax, sodium tetraborate, Na2B4O7.10H2O, colmanite or calcium borate, Ca2B6O11.5H2O, and kernite, Na2B4O7.4H2O. In India, borax occurs in Pagha Valley, Ladakh, and Sambar Lake, Rajasthan. The abundance of boron in earth crust is less than 0.0001% by mass. Two naturally occurring isotopes of boron are boron 10, 19%, and boron 11, 81%. Aluminium is the most abundant metal and the third most abundant element in the Earth's crust, 8.1% by mass, after oxygen, 46.6%, and Si, 27.7%. The important minerals of aluminium are bauxite, Al2O3.2H2O, and cryolite, Na3AlF6. Gallium, indium, and thallium are less abundant elements in nature. The boron family include the semi-metal boron B and the metals aluminium Al, gallium Ga, indium In, and thallium Tl. This group contains metals and metalloids. Atomic radii. Atomic radius increases down the group. Thallium has the largest atomic radius. However, there is one deviation. Atomic radius of gallium is less than that of aluminium. The 10 electrons in gallium offer only poor screening effect for the outer electrons from the increased nuclear charge in it. As a result, the atomic radius of gallium, 135 pm, is less than that of aluminium, 143 pm. Ionization enthalpy. Ionization energy decreases going down the group because the electrons are farther from the core and therefore are easier to remove. The decrease in enthalpy from boron to aluminium is due to increase in size. Increase in enthalpies from aluminium, gallium, and from indium to thallium are due to low screening effect of d and f electrons for the outer electrons to compensate the increase in nuclear charge. Electronegativity. Electronegativity first decreases from boron to aluminium and then increases gradually up to thallium. Physical properties. Boron differs from the other group members in its hardness, refractivity, and reluctance to participate in metallic bonding. It is extremely hard and black-colored solid. It exists in many allotropic forms. Boron has very high melting point because it exists as giant covalent polymer in both solid and liquid state. Gallium with unusually low melting point, 303 K, could exist in liquid state during summer. Boiling points of these elements show a regular decrease down the group. Due to its high boiling point, 2676 K, it is used for measuring high temperatures. Density of the elements increases down the group from boron to thallium. Chemical properties: oxidation state and trends in chemical reactivity. The boron family exhibits oxidation states +3 or +1. The +3 oxidation states are favorable except for the heavier elements such as thallium, which prefer the +1 oxidation state due to its stability. The sum of its first 3 ionization enthalpies of boron is very high. This does not allow boron to form +3 ion. That is why boron forms covalent compounds. In gallium, indium, and thallium, both +1 and +3 oxidation states are observed. The M3+ state for gallium, indium, and thallium is energetically less favorable than Al3+. The relative stability of +1 oxidation state progressively increases for heavier elements: aluminium less than gallium, less than indium, less than thallium. In thallium, +1 oxidation state is predominant. The compounds in +1 oxidation state are more ionic than those in +3 oxidation state. In trivalent state, example boron in BF3, there are only 6 electrons around the central atom. Such electron-deficient molecules have tendency to accept a pair of electrons to attain stable electronic configuration and thus behave as Lewis acids. The tendency to behave as Lewis acid decreases in moving down the group. BCl3 easily accepts a lone pair of electrons from ammonia to form BCl3.NH3. AlCl3 achieves stability by forming a dimer. The basicity of the elements also increases in proceeding down the group. Reactivity towards halogens. All 4 of the heavier group 13 elements, aluminium, gallium, indium, and thallium, react readily with the halogens to form trihalides except TlI3. 2m solid plus 3x2 solid liquid gas give 2mx3 solid or M2x6. Of the halides, only the fluorides exhibit behavior typical of an ionic compound. They have high melting points greater than 950 degrees Celsius and low solubility in nonpolar solvents. In contrast, the trichlorides, tribromides, and triiodides of aluminium, gallium and indium, as well as TlCl3 and TlBr3 are more covalent in character. In water, the halides of the group 13 metals hydrolyze to produce tetrahedral MOH4- species. 2Al solid plus 2NaOH aqueous plus 6H2O liquid give 2Na plus AlOH4 whole minus aqueous sodium tetrahydroxoaluminate 3 plus 3H2 gas. The halides of the heavier metals, indium and thallium, are less reactive with water because of their lower charge to radius ratio. Instead of forming hydroxides, they dissolve to form the hydrated metal complex ions octahedral MH2O whole 6 whole raised to power 3 plus. Reactivity towards air. All the heavier group 13 elements react with excess oxygen at elevated temperatures to give the trivalent oxide M2O3, although Tl2O3 is unstable. 4M solid plus 3O2 gas give 2M2O3 solid. Amorphous boron and aluminium metal on heating in air form B2O3 and Al2O3 respectively. With dinitrogen at high temperature, they form nitrides. For example, 2B solid plus N2 gas give 2Bn solid. Thallium favors the formation of oxide over trioxide. Boric oxide, formula B2O3, is acidic. The next three oxides of aluminium, gallium and indium, formulas Al2O3, Ga2O3 and In2O3, are either acidic or basic, and thallium oxide Tl2O3 is wholly basic. Al2O3 and Ga2O3 are amphoteric. Reactivity towards acids and alkalis. Aluminium, being amphoteric in nature, reacts with both mineral acids and aqueous alkalis. Aluminium dissolves in dilute HCl and liberates dihydrogen. 2Al solid plus 6HCl aqueous give 2Al3 plus aqueous plus 6Cl minus aqueous plus 3H2 gas. It also liberates dihydrogen with aqueous alkali. 2Al solid plus 2NaOH aqueous plus 6H2O liquid give 2Na plus AlOH4 whole minus sodium tetrahydroxoaluminate 3 aqueous plus 3H2 gas. Boron does not react with acids and alkalis even at moderate temperature. Thallium seems not to react with air-free water. Thallium metal tarnishes slowly in moist air or dissolves in water to give poisonous thallium I hydroxide. 2Tl plus 2H2O liquid, give 2TL OH aqueous plus H2 gas.